wanted to present, just to give you a little more of an in-depth overview of this model or this report I put out of kind of pulling together conceptual models for ozone formation in the Great Lakes region. I gave, a high-level summary of the report in one or two different meetings. This is a technical report. We released it in February. It's available on our website. It's about 135 pages with a small appendix. And it's not cutting edge work. What it really is doing is it's pulling together and synthesizing our current understanding about what's driving ozone formation here in this region, and putting it into a form that we're hoping that you all can use, the states can use in your SIPs. So it organizes and pulls together findings from a lot of different sources, including some classic studies, some understanding we've had for decades. There's some new insights and slightly different views on our understanding that we've gained from more recent studies. And I have some new analyses that I've done myself. Again, it's mostly kind of packaging what we already know and understand into a form that you all can use and just, excerpt into your SIPs, like as an attachment to a SIP submittal. So we have, and I'm going to go over the outline, but we have at the end of the report conceptual models for each non-attainment and maintenance area. And the idea is that you can just take this and stick it as an attachment or stick it as a chapter of a SIP. They're posted as a PDF, but I can, we obviously have a Word document. I can provide a Word document, which is obviously going to be easier probably for you to incorporate into your SIPs. So that's kind of the goal. And I'm going to go over things, and some of this is going to be, quite familiar to you. Some of it I think might be a slightly different way of looking at things than what you're used to. So the report is organized. There's an executive summary, there's an introduction, and then the kind of two substantive chapters are the focus on the whole region is looking at drivers of ozone formation. So looking at meteorology, transport, emissions and concentrations of precursors, NOx and VOCs, and looking at ozone formation chemistry. And then the third chapter looks at the trends, concentrations and trends in ozone, including like distribution of ozone in the region, trends, and then doing meteorological adjustment of ozone and looking at those met-adjusted trends. And then the conclusions for that kind of pull the second and third part together and looks at the role of drivers in creating ozone patterns and trends. And then what we have is, I have these, I was talking about the conceptual models for each area in the region that pulls together just for that area. This is, again, fully intended to be used in SIPs, just pull out, stuck in a SIP. Includes for that area, what's the meteorology and transport, ozone precursor emissions and trends, formation chemistry, trends in ozone concentrations and origins. And they have these models for the major urban areas, non-attainment areas, Chicago, Detroit, Cleveland, St. Louis, Louisville, Cincinnati. And then there's one for the Wisconsin Lakeshore and one for Western Michigan. So what I want to do today is step through the drivers, step through ozone concentration and trends. And then I'll just remind you again about the conceptual models for each area. So kind of starting off looking at the meteorological drivers. This figure is from a research paper published by EPA in 2007, looking at the different factors and kind of the impact of different factors on ozone formation. So actually for Cleveland, and this is, as I said, done by EPA using a generalized linear model. And what you see with the y-axis is the log of the impact of that factor, temperature, maximum temperature, relative humidity, the impact of the value of that temperature on ozone. So positive values means it's increasing ozone, negative values meaning it's decreasing ozone relative to the mean. And so you see, not surprisingly, for temperatures over about 20 degrees C, maybe 15 degrees C, increasing temperatures increase ozone. That's our basic understanding. And that holds true here. So we get the highest ozone at the highest temperatures. Relative humidity is the opposite impact. We get the highest ozone at lowest relative humidities, and ozone actually decreases as humidity goes up. And that's kind of also consistent with our general understanding. Transport distance. In other words, I think this is probably like over 24 hours. In this case for Cleveland, they got the highest ozone with the least amount of transport. And then they got the most ozone with westerly winds. So the fact that they got most ozone with high temperatures and low relative humidity, this is pretty universal. We see this in most sites. You know, you increase temperature kind of around the world, you're going to get more ozone. But the fact that you got the most ozone with little transport and with westerly transport, that's site specific. These things vary from site to site. You know, we know there's some sites in Lake Michigan that need a lot of transport to get high ozone. So these are site specific. These are pretty universal. So then this figure is, I made this figure based on data provided by EPA as an updated version of the previous analysis using a generalized linear model. This map shows the most important factor, like the number one most important factor driving high ozone around our region. These factors are 24-hour transport direction, maximum temperature, a little confusing. This is T here is transport, T here is temperature. The deviation in temperature at 850 millibar pressure, deviation in temperature, deviation from the mean, 925 millibar. Average midday relative humidity and solar radiation. And what you see is that we have different factors that are most important in different parts of the region, and these vary systematically. So the southern part of the region, the average midday relative humidity is the most important factor. So, you know, we know, as we saw previously, that high relative humidity decreases ozone. So basically, these sites, the most important factor is the relative humidity. And in fact, having low relative humidity is most important in the southern part of the region. Most of the region, this kind of pinky orange and then these two orange colors, is temperatures, either maximum temperature or deviation of temperature from the mean. So most of the region, you know, in particularly the northern part of the region, temperature is the biggest factor, with the exception of kind of the northern part of Lake Michigan, where the 24-hour transport direction is most important. So, you know, this fits kind of our general understanding is that transport is really important around Lake Michigan. Temperatures are really important generally. And then, I mean, I actually hadn't really fully grasped that relative humidity is actually more important than temperature in the southern part of our region. So that, the report also shows the second most important factor and has similar maps based on the CART analysis, classification and regression tree analysis that I've done. And that actually, the findings from the CART are actually very consistent with these findings, which is encouraging. So that's kind of just the weather, the different factors of weather. If we look at the synoptic weather, kind of the larger scale weather patterns, we have two main types of synoptic weather patterns that really are most common in high ozone days. First is stagnant conditions. So under these conditions, you know, you're not having a lot of winds, emissions are staying near their source and building up to really high levels. These tend to lead to peak concentrations in the urban areas close to the emission sources. If you have stagnant conditions, these episodes can last for many days and have building ozone concentrations over that time period. And they can also lead to, because these kind of calm, stagnant, hot conditions tend to occur over a wide area, we can have high ozone concentrations in urban areas over, you know, the whole LAGCO region with this kind of an episode. And then the other type, of course, is lake-driven transport, which is especially important in Lake Michigan. Transport-driven events, kind of like what we saw transport was most important in the northern part of Lake Michigan. These tend to lead to episodes where we have high ozone confined to a more narrow area, kind of right around the lake, where stagnation events can be much more widespread. And of course, you know, the patterns, we have morning winds that'll carry emissions from Chicago, Milwaukee out over the lake and other regional sources over the lake. And then we have those precursors reacting in the stable marine boundary layer, moving northward and then being pulled on shore, usually by lake breeze. So that's these are kind of the overall synoptic weather patterns. And there's this classification of synoptic weather patterns that's been developed. And this, I should have put the reference to I did this analysis, but based on this classification that's put out by some researchers. The citations in the report, but they're classifying different days when you have different kinds of weather patterns, and these are classified primarily by their humidity. So dry or moist are the two most important for ozone. And then the temperature. So moderate, is kind of warm temperatures, tropical is hot temperatures. And so what we see is that, and these are for exceedance days, ozone exceedance days in the different non-attainment areas. And what you see is that tropical or hot weather accounts for most of the exceedance days. These are, most of these, the orange, yellow, green are tropical, excluding this little one here. So most of the, mostly we need hot weather. We do have some dry moderate, in other words, warm days that are important, particularly in southern areas and in Michigan. So Cincinnati, Louisville, look at the orange bars, Cincinnati, Louisville, St. Louis. And then interestingly, some of the Michigan sites as well. If you remember back, the EPA's GLM was saying relative humidity was more important than temperature in the South. And so we're kind of seeing that we need warm temperatures, but dry. It needs to be dry in the southern region. Michigan, we didn't see the same thing from the GLM, so this is a little kind of a different pattern. And then we see that humid or moist weather actually accounts for about half, 40 to 70% of exceedance days, more in the south and east. So our humid or moist patterns are these kind of oranges and yellows and greens. So kind of over here, they're more important. So then I want to look a little bit at lake breezes because they are so important in parts of our region. Other parts of the region, obviously not relevant. Cincinnati there's no giant lake there, but Lake Michigan, Lake Erie, Detroit. This is a schematic based, modified from Foley et al. You may have seen it before, but just showing you a schematic of the land breeze and lake breeze pattern. So the idea is that overnight, and in the early morning, you can have the lake is warmer than the land. And so the air is going to rise over the lake, and then it's going to pull air from the land over the lake, and you get this kind of cell here forming here. That's what really brings emissions, also synoptic wind sometimes, but can pull emissions from Chicago, for example, out over the lake. And then what happens is you have a shift in the wind breeze. Like then once the land starts warming up, then the land's gonna be warmer than the lake, and then you get the reverse flow. And then you get these sort of cells forming the reverse direction. So the kind of key components of a lake breeze, first is that you have an offshore breeze switching to an onshore breeze. That's an important component. You also have, during the lake breeze period, you have divergence over the lake. You have winds moving away from the center of the lake, and you have the same thing happening on the other side. And then you have convergence onshore, where the lake breeze meets kind of ongoing synoptic winds. So that's kind of another key component. And then you tend to get ozone formation in a shallow marine boundary layer, which can actually be much shallower than what we are showing here. Some of the research from Elmas and other studies have found that, that can be combined to the bottom 50 to 100 meters. And I've rarely seen it go as high as 1,000 meters. So key components, offshore to onshore, wind switch, divergence over the lake, convergence onshore. So now if we look at Lake Michigan, or we have done the most work over Lake Michigan, we have the best understanding of what's happening over Lake Michigan. So we're going to look at, this shows Kenosha, 2 sites in Kenosha. One CP is Chewauquee Prairie, right on the lakeshore. Kenosha Water Tower is about 3.5 miles inland from the lakeshore. And then Holland, Michigan, across the lake. And what you can see here, this is ozone, wind direction, temperatures, wind speed. On one day, this is a really high ozone day in June. It's during Elmas 2017. And what you see is that you see very clear shift from offshore to onshore flow. Happens first at Chewauquee Prairie, switching from about 240 degrees to 150 degrees wind direction. Very clear shift. And then that same shift happens a few hours later at the inland site at Water Tower. Very clear shift. Temperatures drop at Chewauquee Prairie at the lakeshore site. We have a clear drop in temperature, about 10 degrees, when those winds shift to onshore. There's actually a drop in ozone temporarily, but then you really need that wind shift to get to the really high ozone concentrations later in the day. And what we see is if you look at the radar, if you look at the satellite image, there aren't really many clouds, so you can't really see that classic lake breeze pattern. The classic lake breeze pattern, I'm going to show one later on, but you have clear wind, clear air right around the lake, surrounded by often by these stratocumulus, or sorry, cumulus clouds that can help define that. But you can't see it if you don't have those clouds. But if you look at the radar, that convergence front on this day showed up really clearly. You see this line around the lake is clearly showing the convergence front. And then these are model winds. And the model winds clearly show divergence over the middle of the lake and then convergence along the lake shore. So we have this kind of have a wind shift here. We have divergence over the lake shore. We have convergence kind of shown in two different ways along the Wisconsin lake shore. What's interesting then, if you look at Michigan, you don't have as strong a wind direction shift. And that really, I think this is probably the wind direction shift to the lake breeze here. That really is because the synoptic winds here are kind of coming from the west-southwest. And that's actually onshore flow for Michigan. So you actually don't need that big of a wind direction shift in Western Michigan to kind of get the ozone to be pulled onshore. So we don't have as strong a wind direction shift. And we don't really see as strong a convergence front. You can see a little bit down here. Sometimes you see it, but it's not as important. And again, it's because the synoptic winds kind of add on to the lake breeze winds. So this day we did have a lake breeze, but it wasn't as clearly defined along Michigan as it was on the Wisconsin coast. And that's actually not unusual. So that's kind of Lake Michigan. And if we look at the wind directions during high ozone hours, we kind of see this. We see that Kenosha, Chilwaukee Prairie has winds from the south-southeast. You know, Kenosha Water Tower, they're shifted a little more to the southeast. And Holland, Michigan, on the Michigan coast, has southwesterly winds. And that's kind of because we're talking about, you can see it here, we really do have Chicago as the main contributor. And so you have to have, you know, a pretty strong westerly component of winds to get the ozone over to Holland, whereas with Kenosha, the southerly component is more important. If we look at Cleveland and look at Lake Erie, I want to just look at the lakes and their just kind of some of their geography and physical structure before we jump into looking at lake breezes here, because I think that just this map of bathymetry and the orientation of lakes explains a lot. So we see Lake Michigan here. It's really pretty deep. You know, we have some very deep, you know, down hundreds of meters deep in different basins of Lake Michigan, whereas in Lake Erie it's much shallower. It's about half the surface area, and I think it's about a quarter or less, maybe only 20% of the volume of Lake Michigan. And what that means is that Lake Erie heats up much faster in the spring. It actually gets colder in the winter and freezes more in the winter, but in the spring it gets it gets hot much faster, which means that there's less of a drive for lake breezes. Getting weaker lake breezes because your lakeland temperature differences are much smaller. Also, it has a long axis running in a different direction. So Lake Michigan has this, you know, pretty straight north-south and slight tilt axis to it, whereas Lake Erie is oriented kind of, you know, south-southwest and north-northeast. Which means it's going to have really different interactions with synoptic winds, which are primarily from the west or southwest. It's going to kind of, synoptic winds are going to kind of line up with the lake, whereas here you need kind of more shifts involved. Lake Erie also has its main emission source, Cleveland, on the kind of south in kind of in the middle of the lake, where Chicago's kind of sitting here at the one end of the lake. So things can really get channeled up the lake. Whereas here, you know, if you have a westerly wind, it's going to blow Cleveland emissions this direction, and it's not really going to impact this part of the lake at all. In addition, Cleveland's a much smaller city than Chicago, and so we're going to have fewer emissions as well from here. So there's a lot of different factors that ultimately lead to lake breezes being a bit less important on Lake Erie than they are on Lake Michigan. So I did look at the lake breezes in Cleveland on a number of years. And we do have lake breeze days on high ozone days. High ozone days are split about 50-50. It's different from year to year, but about 50-50 between days with a lake breeze and days that don't have a lake breeze, that really just have a synoptic winds. Lake breeze days, this is one example. You see, this is that clear lake breeze pattern, the satellite I'm talking about, where you have, you can very clearly see the lake breeze fronts where the winds are pushing outward, coming onshore and converging. So these are our convergence fronts. Very clear there. If you look at the winds from the model, you see the same kind of thing. You see the winds. In this case, they're coming from the west-northwest, which is, a different direction than what we see in Lake Michigan. And actually the lake breeze days are split between days with this kind of west-northwesterly winds and days with kind of north-northeasterly winds, this kind of direction. You see that down here. These are high ozone hours, and you see the winds came from this direction or kind of this direction. And then we do see divergence over the lake here and convergence onshore. And then this is looking at the ozone temperature, wind direction, wind speed on this high ozone day. And I think these are the hours with the lake breeze. It's not as strong a shift as what we saw in Lake Michigan, but there is still, that's well, it's, pretty close to 100-degree wind direction shift. So that is actually a pretty big shift here. Days with synoptic winds. This is one day we just had, synoptic winds blowing. They tend to come from the southwest, west, or northwest, north-northwest. And I looked at Toledo also, and Toledo high ozone days are mostly not impacted by lake breezes at all. I looked at 8 high ozone days in 2021, 2022. Only one day had a lake breeze. The other 7 were impacted just by synoptic winds. Then if we shift to look at Detroit, Detroit's kind of sitting down here. It's really complex geography. We have Lake St. Clair, Detroit River. The whole Detroit area extends up here to Port Huron. So there's the St. Clair River up here. I think that's the right name. And Lake Huron, it's really complex geography. And that's going to lead to a lot of complexity in lake breeze fronts and ozone formation and transport. Also, Lake St. Clair is really shallow. Western Lake Erie Basin is really shallow as well. So if we look just at the 3 sites that have winds along the Detroit non-attainment area, we have somewhat different wind directions. So all of them have a southerly component, but Allen Park here gets high ozone when winds are from the south-southeast, which is basically coming right over Lake Erie. And it does generally look like Allen Park is most affected by lake breezes. The site of these 3 that's most affected by lake breezes coming from Lake Erie. Detroit East 7 Mile, kind of downtown Detroit, is located down in this direction. So the high ozone in Detroit East 7 Mile mostly comes from downtown Detroit. Not a big surprise there. And Port Huron up here, the winds during when ozone's really high are coming from the south to southeast. So kind of coming right from Detroit or kind of traveling up the river here from Lake St. Clair. And generally, I already kind of said this, but generally Allen Park seems to be the site that's most impacted by lake breezes. And these are lake breezes coming from over Lake Erie. And our source apportionment modeling actually suggests that this site has more contributions from Ohio because of these patterns. The Detroit East 7 Mile site is less frequently impacted by lake breezes, but is still sometimes impacted. And those can come either from Lake Erie or from Lake St. Clair. And Port Huron seems to be mostly affected by synoptic patterns. And we can look at this one day as an example. We do have, pretty strong divergence over Lake Erie with kind of winds that here are driving up, to affect the Allen Park monitor and also affecting East 7 Mile. At this point, they're not really reaching Port Huron. If you look at the satellite image, the satellite suggested that Lake St. Clair is also having a lake breeze, and you have this convergent front here between the Lake Erie lake breeze and the Lake St. Clair lake breeze. The model can't capture that. And then if you look at the ozone temperature, wind direction, wind speed at the monitors, we had a lake breeze at Allen Park for a good long while, for maybe 10 hours or so, 8-10 hours, something like that. We had a lake breeze for a shorter time period at East 7 Mile. And it looks like we actually did have a lake breeze at Port Huron, but it hit really late after ozone was already dropping. And so it didn't really affect the ozone at that site. Another point is that, like I already mentioned, this is a really complex area for the geography, and it looks like the lakes often influence the winds without really developing a true lake breeze, where you have this full, cycle, full cell, um, with return flow and everything. But often, you can kind of see the lakes kind of bend the winds. I think it's not a true lake breeze, but they are impacting the winds. So I did look at transport in a number of different directions, including looking at pollution roses, looking at back trajectories and everything. I'm only going to show the results from our modeled source apportionment because they actually agree pretty well and they synthesize a lot of that information. So this is a lot of information. We have the different non-attainment areas. These are the Wisconsin sites, Chicago, Michigan sites, Detroit, Cleveland, Columbus, and so on. These are different. This is base 2016 source apportionment. And we had this year, we were able to break it down by like sub portions of states. So it's not just Illinois, but we also were able to look at the Chicago metro and suburbs area, Chicago exurbs, East St. Louis, Indiana. So we have kind of a finer breakdown here. And what we see if we look at this is that transport from outside the local area is most important for downwind sites along Lake Michigan. So our Wisconsin sites, including Milwaukee, by far the largest contributor to these sites was the Chicago metro area, this purple area, by far. Same thing for Michigan. Michigan was really impacted by Chicago metro and suburbs and northern Indiana. Northern Indiana is important for Wisconsin, but a bit smaller. Chicago, but for all the other urban areas, all the big urban areas, kind of besides Milwaukee, the localized emissions are the most important source. So Chicago, ozone mostly comes from Chicago. I should say it's not mostly, actually. If you look at the proportion, we have a lot of background and biogenics and other things here. But if you're looking at the anthropogenic sources, most of the anthropogenic ozone comes from Chicago. Detroit is mostly coming from Detroit. Cleveland's mostly coming from Cleveland. Columbus, mostly from Ohio. We didn't do a Columbus tag. Cincinnati is mostly from Cincinnati and Kentucky, which was modeled together. Louisville is mostly Kentucky, and so on. So for most of the big urban areas, the largest anthropogenic source is local. And this is confirmed by pollution roses and back trajectories, where is also consistent with the finding that stagnation events where you're not having a lot of transport are most important for our urban areas. But transport is really important for the Lake Michigan sites. And as I mentioned before, all areas do have some impact from upwind sites. I'm not saying that there's no impact to transport, but the main source for our urban areas is more localized emissions. Okay, shifting gears now and looking at ozone precursors. So you all are familiar with this kind of a plot. This is looking at the emissions or the emissions inventories for NOx on top and VOCs on the bottom. I just chose Ohio and Wisconsin as examples. I'm showing the major sources. Anything that contributed less than, I think, 1% is looped, put together in the other category. Large emission reductions, both NOx and for VOCs from all states. So we had 68 to 76% reductions in NOx, mostly from EGUs, highways, and off-highway vehicles. Smaller but still significant reductions in VOCs, 41 to 67% reductions. Most states had about 53 to 55% reductions, with a few outliers above and below. Those reductions mostly solvent utilization, off-highway and highway vehicles. No surprise either. This is from LAGCO modeling. We had the largest NOx emissions in the urban areas and along highways. VOC emissions are split between urban VOC emissions and biogenic VOC emissions from forested areas in the south and kind of up in the north too. Again, no surprises there. If you look at projections, these are LAGCO modeling projections into the future. Just showing for Indiana as an example. We have NOx here, VOCs here. They're projected to decrease, but by less than what the rate we've been having before. So NOx is decreasing, but again, at a slowing pace. projected to have 28 to 38% NOx reductions out through 2028, mostly in on-road and EGU emissions. And VOCs were projected to have just a 5% VOC reduction, so much smaller reductions than we've seen. And shifting gears again, so we're looking at ozone precursors still, but now we're looking at the monitored concentrations. And I'm showing NO2 concentrations for St. Louis as an example. The report has them for all the areas. This is all the monitors that monitored NO2 for at least 5 years. And they're color-coded by the monitor. And one thing to point out is that the dashed lines are the near-road monitors here. There are 2 near-road monitors in St. Louis. Everything else is not a near-road monitor. And what we see generally is that we see about 58 to 71% reductions in NO2 concentrations, annual average, actually summer NO2 averages from 1995 to 2021. These are really similar to the reductions we project in the emissions, which is great. It looks like our monitor concentrations are going pretty well at a large scale with our emissions reductions. We had especially large reductions in the mid to late 2000s, kind of in this time period. You see some sharp drops. And that's because there were so many control programs that were implemented in that time frame. There were vehicle standards, there was the NOx, some of the NOx trading programs, NOx zip call. There were a lot of programs implemented in that time frame that really reduced NOx emissions. And we see it in the concentrations. It does look like concentrations are still decreasing, but they're decreasing more slowly than before. And it's also noted in basically all the areas, the near road monitors tend to have the highest or among the highest concentrations. VOCs are a lot harder to get at, mostly because we just don't have that many monitors. They're much sparser over space. They're much sparser over time. You know, most of our monitors, a lot of the PAMS monitors only monitor June through August, and a lot of them measure every 6 days. So we have, you know, one measurement every 6 days, a 24-hour average. Whereas NO2, we have every hour, you know, year round generally. And even NO2, we don't have great spatial coverage. So to try to look at, try to make sure I'm looking at meaningful trends and not just variability, what I'm looking at here is a 5-year average of the measured hydrocarbons. These are in the summer. And we also have, you know, monitors measure different numbers of compounds. We have the standard PAMS monitoring suite is like 50 some compounds. There are many more compounds out there that we could possibly monitor, but it's just really tricky to do. So some years, some sites were measuring, you know, more than 45, 50 compounds. Sometimes we're measuring 7 compounds or something. It didn't graph anything that measured less than 7 compounds. So it's kind of complicated. The thickness of the line corresponds to the number of compounds measured, the number of VOCs measured. So put more weight on these nice thick lines that are measuring, you know, a lot of compounds. But it's still like this site in Indiana, or is that, I think it's Indiana, measured, you know, only 7 to 15 compounds, but it was consistent across this whole time period, and we could see a pretty strong decrease. So that's still meaningful information to have. So we have these sites, you know, we have this monitoring in a number of different areas. And generally, we see decreases through the late 2000s, you know, kind of through around here. But then in most sites since then, concentrations have kind of leveled off. You know, here it goes up and then back down. Here it's decreasing, and then we don't really have good data for this last time period. We see this across the areas. This does not agree with the inventories. The inventories show that VOCs are still decreasing, and this is showing they've been flattening out. Is maybe an issue with the inventories. They might be missing some important compounds. It's also possible that we're just not we're definitely not measuring all the compounds. It's possible that some of the unmeasured VOC compounds may be decreasing still and may be agreeing with the inventories more. So we don't have great measurements, and there may be issues with the inventories as well. We don't really know. And this is something, hopefully there's going to be a big field campaign over Chicago this summer looking at VOCs, so we might get some more information about this out of that. Switching to carbonyl VOCs, a different kind of VOCs. These carbonyls come from 2 sources. They can come from oxidation of other VOCs or from primary emissions, meaning being released directly. I'm really just looking at formaldehyde and acetaldehyde here. We do also measure acetone, but acetone has a lot of complex sources, so I didn't include it. You see, pretty big reductions through the 2000s. Sometimes there's minimum in the early 2000s, and minimum in the late 2000s. But we actually, in Chicago and Detroit, we see some pretty clear increases in carbonyls since then. Milwaukee and St. Louis show kind of flattening trends. This increase could be due to increased oxidation of other VOCs. Could be due to increased biogenic VOC emissions due to increasing temperatures. I did look at isoprene concentrations. I'm not going to show right now, but they might be increasing very slightly. It's hard to tell. It could be noise too. Could also be due to unknown changes in chemistry or meteorology, but they kind of come back to the fact that our monitor concentrations aren't really agreeing with our inventories here. For the very few sites where we have concentrations, this is 3 sites in Chicago for the entire city, 3 sites in Chicago. That's not very much. That's kind of our ozone precursors. So I'm going to give just a high-level summary of what I figured out about ozone formation chemistry. I think a lot of you were on the report I gave about the ozone formation chemistry report. So I put a lot of work over the last few years into trying to nail down ozone formation chemistry. And this is just a summary of those results. So what we have for St. Louis, for example, we find that basically the whole St. Louis area is NOx sensitive with some transitional chemistry downtown. Most of the areas are like that. Louisville's like that, Cincinnati's like that, Detroit's like that. It's a little like transitional area to the northeast. Cleveland's like that, some transitional area along the lakeshore. Wisconsin lakeshore is, NOx sensitive with transitional chemistry in downtown Milwaukee and some along the southern lakeshore. Western Michigan's all NOx sensitive. Chicago's the one real big outlier. That Chicago still has a very large area that's NOx sensitive and kind of shifting to transitional chemistry in the central 60 kilometers or so, kind of surrounded by a donut of transitional and NOx sensitive chemistry outside there. So we're going to talk in the next section kind of about how this chemistry, the impact of meteorology, emissions, and everything are influencing ozone. So that's kind of shifting gears now. Then we want to look at ozone concentrations and trends. And as I just mentioned, we want to look at how the formation drivers are affecting the distribution of ozone, affecting concentrations of ozone, and affecting trends in ozone. So this map, you all have seen this very many times, I'm sure. So pink areas are non-attainment areas. Hatch pink, hatch blue are maintenance areas. And we see, high ozone in urban areas and then along the Lake Michigan lakeshore. So in urban areas, we get high ozone there because that's the concentration of emission sources. We have the most emissions in these urban areas. We have, biggest episodes when we have stagnant meteorology. And, if you have VOC sensitivity or NOx suppression, you can end up with the lowest ozone in the city center, which currently we really only have strongly in Chicago. Then we also have high ozone around Lake Michigan due to transport of ozone and ozone precursors. The meteorology impacts that with southerly transport and onshore lake breezes. So again, role of kind of meteorology, location of emissions and whatnot, chemistry. We're looking at trends over time. This shows the ozone fourth high values for all the monitors in the region and the design values down here. Again, you've seen these figures before. But if you look at the median value, and the median value for ozone design values decreased by 16% from 2005, from high 70s to mid 60s. That's a big decrease. But it's also much lower than the decreases we found in emissions, which were, much larger than this, on the order of 50% during this time period. I think I went back to 1995 before, so longer time period for emissions, but most of the decrease here is happening in the first part of the period, and we've had things being much flatter over the last 8 or so years. That said, median ozone design values are close to their all-time lowest values. Like 2021 is maybe like the median value, at least was lowest. Design value is lowest then, but we're very close to our all-time low value. But we still have a quarter of our monitors that are violating the 2015 ozone max. So looking at these patterns, we have meteorology contributing to the interannual variability And then emission reductions are leading to long-term reductions in ozone. Another way of looking at this is by looking at the controlling monitors. In other words, the highest value in each non-attainment area. And that's what's plotted here, the maximum ozone design value within a non-attainment area, shown by color. It's very messy, but I'm going to point out two things. First is that the design values often move in concert, kind of in tandem. And that's, because, for example, 2012 was hot everywhere. So we had high ozone in 2012 across the entire region. 2010, well, this is a design value, it's a 3-year value, but we had cooler weather 2009, 2010, and this is during the recession as well. So that affected everywhere. So generally, the patterns kind of track across the whole region. But the relative severity of the problems in different areas has changed. So if we look at Milwaukee and Chicago, for example, Milwaukee's the red line, Chicago's the orange line. A little hard to see in here, but they're, back in 2006, they were within the circle, kind of on the low side. And then 2022, they were near the top. So that, basically relative to other areas, Milwaukee and Chicago have improved less. And that's partly because we know we have Chicago's shifting from VOC, strongly VOC sensitive, towards less NOx suppression, less VOC sensitivity, more towards transitional. Milwaukee has made that transition as well, so that's part of the issue. There's also, things going on with the overlake plume that's reaching Wisconsin. In contrast, if you look at Cincinnati and Columbus, they were among the highest back in the early part of the period, 2005, and they're currently, the lowest. They're currently way at the bottom. Columbus has been redesignated for many years. Cincinnati was just redesignated. So this is also the chemistry, different chemistry here. These have become very strongly NOx sensitive, and as NOx emissions have decreased, they've responded very strongly. So that's kind of just an interesting observation, I thought. I mentioned that we are going to look at meteorological adjustment of ozone trends. So this is starting off with similar results from EPA's generalized linear model from Wells et al. And I want to draw your eye in particular to the solid red line. This is the meteorologically adjusted 98th percentile ozone value. Top plot is for Minnesota, Wisconsin, and Michigan, along with Ohio. Bottom includes Illinois, Indiana, Ohio, as well as Missouri, these other states nearby. So this is they use the generalized linear model to do a meteorological adjustment for kind of all these monitors combined together. And what you see is that there's a very clear reduction in ozone concentrations that's actually much larger for the more southern states. The central region had a reduction of 20 ppb over this time period, whereas the eastern central only had 12 ppb. Consistent with what we observed larger reductions in Cincinnati and Columbus compared with Milwaukee, Chicago as well, although Chicago would fit in this region. But basically, we've seen larger reductions in the southern areas than we have in the northern areas. And we also, when you do this meteorological adjustment, you see that the reductions are slowing down as well in more recent time periods, possibly due to changes, slower decreases in NO2 concentrations and emissions, possibly, changing ozone formation chemistry, probably a combination of both of those. There's a lot of things happening in these groups of states. Another way of doing this is the classification and regression tree, the CART analysis that I do, and Donna did before me. And this shows Cleveland on top. And what we see is each of these colors corresponds to meteorologically similar days. So for example, maybe temperatures over 85 degrees and southerly winds greater than 2 miles an hour, or something like that. Basically, each group has similar meteorology. And what we see is if you look at the days with similar meteorology over time, we see some pretty clear reductions in ozone. So that suggests that we do have decreasing ozone when you adjust for meteorology, consistent with what we saw previously. Almost all the areas in the LAGCO region show trends like what we see for Cleveland. The one exception is Cook County. Again, Chicago's different. Cook County, we have most of the day types have increasing ozone over this time period. And that's because this area, as we've talked about before, is shifting from VOC sensitive and NOx suppressed becoming less NOx suppressed, meaning we get increasing ozone. So again, chemistry is kind of coming into play here. So to kind of conclude this whole section, what we're seeing is that ozone is decreasing since the early 2000s in response to decreasing precursor emissions. Ozone reductions are smaller than precursor emission reductions and have slowed in the last decade. And if we're looking at kind of the connections between the drivers and what we see in ozone, we see, meteorology is driving day-to-day variability as well as interannual variability. Transport and location of emission sources drive the geographic distribution, with kind of lake breezes coming in there to influence that as well. And then emissions and ozone formation chemistry are driving the long-term trends. Again, none of this is probably a surprise to anyone here who's been paying attention to ozone, but this is, again, just an attempt to kind of package this up into a usable format that you all can take and stick in your SIPs. And as I mentioned before, we have conceptual models that kind of pull all this information together for each individual area. We have them for each of the urban areas and for Wisconsin Lakeshore and Western Michigan. So that's what I have now, and I would love to take any questions.